Welcome you all in my next lecture. So in my last lecture I talked about the notions of differentiability for very simple class of functions, that means functions from R to Rn, that means vector valued functions of real variable. But as I told you that next couple of lectures I will talk about the concept of partial derivative, directional derivatives, then total derivatives, then there is a concept of tangent plane, normal line of a surface, then chain rule and higher order derivatives, that we will see when I will talk about the concept of differentiability for functions from Rn to R or Rn to Rm. Those are the concepts which automatically come. Okay. So before that, just in my last lecture I talked about notions of differentiability from R to Rn and the couple of applications I will discuss, and then I will go kind of discuss about the differentiability from different set of functions, like functions whose domain is Rn but range is R, that means real valued functions of vector variable, or Rm valued functions of vector variable, when functions from Rn to Rm. Okay. So now as I said that, okay, if I have a functions from R to Rm or vector valued functions of real variable, then I already introduced the notions of differentiability. Then like in the real valued functions of real variable, we know that sum of two differentiable functions are differentiable, scalar multiple of a differentiable function is differentiable. Similar sort of algebra is also true, I already discussed in my last class. Like these are the couple of results, like sum is differentiable, not only the derivative. What about the derivative of the sum functions? You can also write in terms of the given function capital F and capital G. Scalar multiplication is also true, dot product and cross product. But as I promised that I think I will prove that how the dot product of two differentiable function capital F and capital G given, and how the dot product is differentiable. Not only that, why the derivative is exactly this kind of form, and similarly for the cross product. Let me see, as I said, you just use the first principle, that's it. That means I want to talk about the derivative of the functions, dot product functions. That means what functions? I am talking about the functions t goes to ft comma gt. Once I am taking the dot product, that means it becomes a real valued functions of real variable. So you just use the definitions. So I want to talk about the differentiability of this kind of functions at the point t naught. You just calculate the corresponding quotients. That means, so this, what is the dot product? This is the notation. So that means this is nothing but ft times gt I am writing. That means ft is a vector in Rn, gt is a vector in Rn, dot product means componentized product and sum it up. So therefore this is nothing but I have to find the limit t approaches to t naught ft gt minus ft naught g naught divided by t minus t naught. That's what the definitions or first principle say. So what you have to do, you just add and subtract, that's it. You don't have to do anything extra. You just add and subtract appropriate term and talk about the limit. Okay, so what I have done is that, so I am just subtracting ft gt naught or capital ft naught gt. So let me see, I am subtracting capital ft gt naught, I am adding, oh sorry, not I am adding here, but I am adding this term. Okay, so these and these get cancelled. I am subtracting and adding. So then these and these get cancelled. I am adding and I am subtracting. So that means full term is nothing but capital Ft times capital GT minus capital Ft naught minus GT naught. So I have done, I've just couple of term added, couple of term subtracted. That's it. Then I make this group and I make this group. So that limit I can break up this plus this. Now what you have to do, you just try to rearrange those terms, nothing else. So look here, so if I have, look about the first term, so this is nothing but, you can write this capital Ft gt minus capital Ft gt naught minus capital Ft naught gt plus capital Ft naught gt naught is this kind of form. And this term, this limit, you can break up into two parts. One is Ft minus Ft naught times gt naught divided by t minus t naught, and this combination, this is Ft naught take common, gt naught minus gt divided by t minus t naught. First one is nothing but this one, and second one, this second one you can break out into two parts. Now look at the limit, what will happen? But what is given? Capital F and capital G as differentiable, that means the limit t approaches to t naught, ft minus ft naught divided by t minus t naught is exist. Similarly, limit t approaches to t naught, gt minus gt naught divided by t minus t naught exist. Okay, then what we look at the first one, I mean you just take this object. Okay, so this limit is exist because capital F is differentiable and it will give you what is f prime at the point t naught. But look at this object, because capital G is given to be differentiable, and I said that if G is differentiable, G is continuous. So what will happen the value of this object. That means limit t approaches to t naught gt minus gt naught. What will be the value? Because capital G is differentiable and hence it is continuous, so therefore this limit is nothing but 0, because t approaches to t naught gt is nothing but g of t naught, and therefore the difference is 0. So therefore this object will give you the 0 limit. What about the second one? Again, you just combine t minus t naught with ft minus ft naught. So this will limit exists, that means this limit will give you a prime t naught, and gt naught is a fixed value, is stay as it is. What will happen here? Ft naught value as it is, you take outside from the limit, and the next limit, that means t approaches to t naught gt minus gt naught divided by t minus t naught, which is nothing but the derivative of g at the point t naught, and limit is exists, so therefore this comment. So therefore this is a prime t naught gt naught plus f t naught g prime t naught. So that is straightforward, just using the first principle. Similarly, the cross product you can also do. So again you have to just calculate this limit ft cross gt minus ft naught cross gt naught divided by t minus t naught. Again in that case also you just add and subtract. So I am just adding this term and subtracting this term in the numerator. So it will be same as it is. So that means you just what you have to do, you just to arrange or club together the term. So therefore this you can write, so ft minus ft naught cross gt, and what about these two terms? So this is ft naught cross gt minus gt naught. Okay, then you just break the limit ft minus ft naught cross gt divided by t minus t naught plus limit t must approaches to t naught ft naught cross gt minus gt naught divided by t minus t naught. And of course then you can easily again use a similar kind of theorem, that this limit is nothing but limit t approaches to t naught of ft minus ft naught divided by t minus t naught cross product of limit t approaches to t naught gt, and of course this also limit t approaches to t naught ft naught times this limit. Since capital F is differentiable, this is f prime of t naught, and capital G is differentiable at t naught given, it is also continuous at t naught, so therefore this is nothing but cross of gt naught. This is a constant value, so this is stay as it is f t naught, and this is nothing but the derivative of g at t naught. So therefore just use the first principle and use the definitions and add and subtract, do some appropriate calculations, you will be able to prove it. Okay, so there is a nice theorem, like once I have the differentiability, then if a kind of two functions I have, and if there is a composition makes sense, what can I say about the differentiability of the composition functions? So that is called the chain rule. So therefore this is differentiation of a composite functions. So let G be a functions, real valued functions of real variable from some subset S subset of R, and suppose you have a capital function capital F which is CD from again some interval CD subset of R to Rn, where S is an open set, such that open interval CD is contained in the range of G. So I need that conditions, because next I want to talk about the differentiation of the functions capital F composed with G. So unless and otherwise composition does not make any sense, I cannot talk about the derivative of the composition functions. Even then if I know the definitions of the individual functions small g and capital F, but I cannot talk about the composition functions unless kind of does make sense. So that is why to make sense the composition functions I need this kind of object. That means that domain of capital F should be in the range of small g. That's what I needed. So this is the domain of capital F, CD, open interval CD, and this is the range. So once this makes sense, if I take t naught is a point in S, g t naught let it be S naught which is a point in CD. Now look at the statement of the theorem. If small g is differentiable at the point t naught and capital F is differentiable at the point S naught, so these two things are there. So I need the differentiability of small g at the point t naught, denote S naught as g of t naught, I need differentiability of capital F at the point S naught. Then once I have these two things together, then I can talk about the derivative of the composite functions. Then the composition functions capital HT, which is nothing but capital F compose GT, which is defined as capital F of GT, is differentiable at the point t naught. Not only that, I can write the derivative of the composition functions in terms of the derivative of the original functions. That means derivative of h at the point t naught, which is nothing but a notation this is, which is same as derivative of capital F at the point g t naught, okay. So and g prime of t naught. But g t naught is what? This is nothing but S naught. So that means this is So that means composition function is differentiable. Not only that, derivative of the composition function at the point t naught, which is nothing but derivative of capital F at the point s naught, which is nothing but g t naught, times derivative of g at the point t naught. Once I have this kind of theorem, then you can see in the next example I'll discuss. If I know that the kind of derivative of two functions, and if I know that composition makes sense, then using this theorem I can talk about the derivative of the composition functions. This is the applications of chain rule. Okay, very simple examples. Take a function g from R to R, which is gt is equal to t square minus 1. It is very nice function. You know this function is differentiable. And take a functions capital A from R to R3. Again, if I take a point in R, it will be a vector in R3, and as I said that it will have R3 has a orthonormal basis consisting of three vectors. One is I cap, j cap, and k cap. So this is my functions I have written. This is I cap plus sine t plus 1 j cap plus e to the power t square plus 1 k cap. Now I am defining a new functions capital H, which is nothing but a composition functions. Capital H of t is nothing but capital F of gt. So now I want to calculate the composition function derivative at the point t using the composition rule. That means you first get the derivative of small g, get the derivative of capital F, and use the earlier theorem, you will be able to say the derivative of the composition functions. So small g is very nice function, you can just calculate the derivative, it is 2t. Capital F is also very nice function, because what are the component functions? First component function is 1, second component function is sine of t plus 1, and third component function is e to the power t square plus 1. Each of the component functions are differentiable. So, and what is the derivative? You just take the derivative of the corresponding function. So, first component function is constant, so therefore the derivative is 0. Second component function is sine of t plus 1. What is the derivative? Cosine of t plus 1. And third component function is e to the power t square plus 1. That is also nice functions. And what is the derivative? You just calculate it, e to the power t square plus 1 times 2t. So, therefore, I can have the derivative of the composition functions. This is by the definitions, right? So, the composition function is differentiable because my function small g and capital F, they are also differentiable. So, therefore, composition function is differentiable. Not only that, I know the derivative of the composition function at t in terms of the derivative of the original functions or given functions small g and capital F, which is nothing but capital F prime of gt times g prime t. G prime t, you know, this is 2t. And what is capital F? Capital F prime also know, at the point t you know the expression, just you replace t by gt. So, that means first one is what? It will give you 0, there is no contributions, forget about that. Only second one, you replace t by gt, that means cosine of t square minus 1 plus 1 j cap plus 2 times replace t by gt, that means t square minus 1, 2 times t square minus 1 e to the power t square minus 1 whole square plus 1. And if I just do the calculations, it is very simple. So, therefore, using the chain rule, you can calculate easily the derivative of the composition function. Okay, one theorem I should say that on AB, open interval AB, the derivative of capital F is identically 0 if and only if capital F is constant. That you know. If I have a functions from real valued functions of real variable, and if I know that function is defined from open interval say AB to R, and that function is identically 0 if and only function is constant, that we know. Similar kind of theorem I can prove in the context of vector valued functions of real variable. That's exactly the theorem. So, let capital F is a map from AB subset of R to Rn. If capital F is constant for all t, this is a constant function, then you can just check that derivative is 0, okay, just using the first principle. And suppose you have a functions capital F from AB subset of R to Rn, and suppose if capital F is differentiable and suppose derivative is 0, then there exists a constant, you can prove that capital F is C for all t, and you can prove it. If it is a constant function, derivative is 0, then you can use the first principle. Converse also you can say that if I have a function which is differentiable and derivative is 0, then also there exists a constant, you can prove that. That means there exists a constant C such that f of t is equal to C for all t. So, that means the derivative identically 0 if and only if the function is constant. You can also have this kind of observations in this setting as well. Okay, so as I said, or as I promised that, okay, I kind of give some applications of, since I have the notions of differentiability of vector valued functions of real variable, then you will see there are a couple of applications, you will have nice applications, okay. So, of course, in particular if I take n is equal to 2 or n is equal to 3, that means R2 and R3, that means I have a R2 valued or R3 valued functions of real variable, then you will have you will see a couple of applications. Okay, before I need to give some applications, I need those concepts. So, what are the concepts? That is called closed curves. So, I know the meaning of curve is a continuous function that I already said, okay. So, let me just kind of recall again once again what is closed curve. So definitions: a curve C in Rn, of course, is closed if C has a parameterization. So curve means, once I talking about the curve in Rn, that means it's automatically, if it has a parameterization, I already talked about that, then you'll have a parameterizations gamma from some closed interval AB subset of R to Rn, which is continuous function that we know. That's exactly I said. A curve C in Rn is closed. Of course, closed comes later. First, the definition of curve you know. So that means, suppose if you have a curve which has a parameterization capital gamma, I will say that this curve is closed. That means the value of gamma at A is same as value of gamma at B. That means if this is my parameterizations capital gamma of the curve C, I will say that this closed. That means it should, that means the value of gamma at the first endpoint, that means small a, is exactly same as the value of gamma at the last endpoint B. So if gamma is equal to gamma B, then I will say that that curve is closed. Of course, as I said, gamma is a continuous function because I already said, that means parameterizations, that means if I have a curve, that means you will have a corresponding parameterization gamma, which is a continuous function from closed interval AB to Rn, because I am talking about curve in Rn. Okay, so note that gamma is continuous. Okay, so what are the kind of examples? This is a closed curve, this is a closed curve, but this is not. Why? Because suppose this is my starting point. Okay, so it goes like that and come back. So these 2 points are different, so it is not closed. Similarly, it is also not closed. One simple closed curve, you can easily see circle. So for example, what is the parameterization? So suppose I have a gamma from say 0 to 2 pi, okay, subset of R to R2, okay. So how do I define? Say gamma t is cosine t plus I sin t, okay. Now at t is equal to 0, what is the value? Gamma 0 is 1, so sin 0 is 0. And at gamma 2 pi, what will happen? Again, sin 2 pi is 0 and cos 2 pi is 1, again 1. So therefore gamma 0 is equal to gamma 2 pi. Okay. So therefore if I draw a picture, it will be like that. So gamma 0 means I am starting with this point, okay, and coming by this. So this is a closed curve. So these are two closed curves, but these are open curves. Okay, I have given some example here, of course, the same thing. So as gamma t is 3 cosine t, 3 sin t, okay, you can draw a picture. And what about the value of gamma at 0 and 2 pi? Both becomes 3, 0. So therefore it is a closed curve. What about this curve? This is not closed. You can draw a kind of picture. So what is the value of gamma at 0? Value of gamma at 0 is nothing but it should be 0, 1, okay. And value of the gamma at 1, what will be that? It should be, that means t is equal to 1, right? So that means this should be 1, 0. So these 2 points are different. Gamma 0 is not equal to gamma 1. So this is not closed. This is a continuous function because it's the component. What are the component function? T is one component function, 1 minus t, and the component function. Component function are continuous function. So this is a continuous function. It is the parameterizations. It will give a curve, but it is not closed because the value of gamma at 0 is not equal to value of gamma at 1. What about simple curve? So a curve C in Rn is simple if C has a parameterization, say gamma, okay, where I is an open interval in R, such that any two interior points t1, t2 of I, if t1 not equal to t2, it should implies ft1 not equal to ft2. That means if I have a curve gamma in Rn, okay, then it will have a parameter. Suppose it has a parameterization capital gamma, I will say that this curve is simple if I take two interior points. That means if I just avoid the boundary points, then if I take any two distinct interior points, that means the gamma should be injective or 1, 1. That means if t1 not equal to t2, gamma t1 not equal to gamma t2. That is, I have written, that is gamma does not have a self-intersecting points except for the end point, that is the terminal point and the initial point can be same. So that means if I have a parameterization say from say 0 to 1 or whatever it is, so if I take t1 comma t2 from open interval 0 1, then I demand that if t1 not equal to t2, then corresponding gamma t1 not equal to 2. That's my demand. But if t1 t2, suppose if t1 t2 taking the values either 0 or 1, so t1 is equal to 0, 1 or t2 is equal to 0, whatever it is. So at the boundary point I do not demand that. Okay, what I demand is that if it is the interior point, if it is not the say terminal point or the initial point, if it is the interior point, then I demand that if t1 is differ from t2, then the corresponding gamma t1 it's not equal to gamma t2. So in the interior it should be injective, but at the boundary point it might happen, then they might equal or coincide, whatever it is. So example, so for example, these are simple curves, okay. So like there is no kind of cross 8 kind of pictures is there. So this is simple, this is simple, this is simple, right? But this is not simple, because if I take here they cut at one point, that means you have one T1, the value is same as another point T2 is same in the parameter. Similarly, you have also, this is not a simple curve. Example I have given, for example, if I take gamma T, again this is just draw it, it's a circle and it is simple curve, because at the end point 0 and 2 pi they coincide. So I don't care about that. But what I do care about is the interior. Interior, you will say it satisfies this kind of property. So therefore it is a simple curve. What about this one, gamma T sin T? So this is actually not simple. Why? Look, so for example, if you can easily find 2 points in between 0 to 2 pi, because these are periodic functions, then this value will be same. So therefore you can check that this is a function which is not simple. Even though it gives a curve, of course it's component function or continuous function, but it is not simple. That means get 2 points T1, T2 which are interior point, that means lies in open interval 2 pi, T1 not equal to T2, but the corresponding gamma T1 is exactly equal to gamma T2. Because of this cosine T and sin 2T, you will get it. So therefore this is not simple, but this is simple curve. There is another concept of curve that is called smooth curve. A smooth curve means what? A curve C, I say that it is smooth if suppose C has a parameterization capital gamma, where I is the open interval AB, or say closed interval or I is equal to, or whatever it is. It is either the open interval or the closed interval or the whole R. Suppose this is the parameterization of the curve capital C. What are the kind of conditions I am pushing? I am saying that okay, gamma prime T exists at each interior point. That means if I take any point T from the interior except the boundary point, derivative should exist. Not only that, derivative should be non-zero at the point. If these things happen, then I will say that my curve C, which is smooth curve actually. So curve, we know, once you have a curve, then with the corresponding parameterization is there. I demand that suppose it is has a parameterization. If I take any interior point, it should be differentiable. That means gamma prime 2 should exist. So curve means what? It is a continuous function, I know. Now here I demand little more. That means if I take any T from the interior, that means either from the open interval, or so if I take I is equal to closed interval AB, then it should T coming from open interval AB. So I demand one step more. That means I demand that it should be differentiable at the interior point. Not only that, derivative should be non-zero. If these things happen, then I will say that my curve is smooth. There are a couple of examples I have given. For examples, this is a smooth curve. You can draw this curve gamma T A cosine T A sin T. It will be a circle, you can easily see, and it is a smooth curve, okay, because these are the component functions, and we know the differentiability of the original functions, because it's a functions from where to where, R to R2, right? So that means in R2 you have two component functions. If the component function is differentiable, then the original function is differentiable. What are the component functions? They are cosine functions, sine functions, very nice functions. These are differentiable functions. So that it is differentiable. The only part you have to ensure that derivative should be non-zero, that you can easily calculate and say that this is also non-zero. So that means this is a smooth curve. Similarly, once you have gamma T replace A by B, that is also a smooth curve. Okay, again you can take, this is a function, this is a combination of polynomial function of T, right? The polynomial function of T, this is a polynomial function of T. So therefore component functions are very nice, these are differentiable. So that means gamma prime T exists for each T interior, and also you can check the derivative is non-zero, okay. So these are all examples of smooth curve, okay. I have just written one part, is that smooth curve is a curve without any sharp corner. So that means it should not have picture like this, sharp. There should be a bend kind of thing, yeah. So this kind of things, I do not want this kind exactly sharp corner, it should not be like that. There should be a small bend like that, because I need the differentiability, and you know differentiability means it should not be sharp, it should be little bend will be there. So that's I have written. So smooth curve is a curve without any sharp corners. Okay, there is a concept called piecewise smooth curve. Of course, from the term you can see piecewise smooth curve means it is not fully smooth, but you can break it into pieces and each piece is smooth. That's so definition means what? Okay, definition I have given: a curve C in Rn is piecewise smooth if C is composed of finite number of smooth curves C1, C2, Cn, as I said. So suppose you have C1, C2, Cn, that means finite number of smooth curve. You just compose it, it becomes a one curve, and this curve I will say that's piecewise smooth. Such that, okay, so I think, so that means the compose mean how to compose it. So I have written such that the end point of Ck is the initial point of Ck plus 1. So that means take n number of smooth curves, join in such a way so that end point of Ck is nothing but the initial point of Ck plus 1, it will give you a curve, and that curve is piecewise smooth. For example here, so this is one smooth curve, this is one smooth curve, this is one smooth curve. Suppose this is C1, this is C2, this is C3. So I am joining C1, the final point of C1 is nothing but the initial point of C2. Final point of C2 is nothing but initial point of C3. So if I have this one, so this is smooth, this is smooth, this is smooth. So but I have only sharp corner, but I do not demand that one. So that means I am just, the full curve is there, I am just breaking into finitely many pieces and each of them are smooth, so it is a piecewise smooth. Similarly this one, it is at a sharp corner, but each of them, this piece, this piece, this piece are smooth, and this is the combinations of smooth curves, so therefore this is piecewise smooth. Similarly, so you can draw something like this is piecewise smooth. You forget about that corner, okay? So this is smooth, this is smooth, this is smooth, but I composed it because the initial point of this is nothing but the final point of this is nothing but the initial point of this one. Similarly, final point of this one is nothing but the initial point, and so on and so forth. So this is a smooth curve. Okay, I have given the examples. Boundary of a triangular region is a smooth curve. Rectangular path is smooth curve. Polygonal path formed by a finite number of line segments, that is also a smooth curve. Smooth means piecewise smooth, I should say, not smooth, piecewise smooth. So that means you have finitely many smooth curves and you have to just compose it in such a way so that the end point of Ck, it should be the initial point of Ck plus 1. If you have joined like that, then the full curve not smooth, but it is piecewise smooth. That means I have a breakup into finitely many pieces and each of them is smooth. Okay, so once I have that one, then I can easily talk about the length of piecewise smooth curve. What is the definitions? So okay, let C be a piecewise smooth curve. Okay, so it is not smooth. Piecewise smooth means that piecewise smooth means I have a finite number of breakup and each piece is smooth. So once I have a curve, then it will have a parameterization. So let it be C is gamma t, t running from closed interval A to B. It is a parameterization. Then the length of the curve C from the point gamma A to gamma B is defined by this object. Because gamma is a function from where? Gamma is a function, suppose I have a piecewise smooth curve in Rn, R2 or R3, whatever it is. That means gamma is a map from closed interval AB subset of R to say R2 or R3 or Rn, whatever it is, okay? Vector valued functions. Then smooth means, of course, piecewise smooth means what? That means it is not smooth on full AB. However, if I take finitely many points out of AB, then it is smooth. That means, and I know the notions of differentiability of this kind of functions from AB to Rn. Okay. So therefore, once I have the notions of differentiability, that means the vector gamma prime t, I know it is a vector in Rn, and then the corresponding norm makes sense. So therefore, once I have a piecewise smooth curve in Rn, then I can talk about the length of the curve. And what is that? What you do, because gamma prime t makes sense, it is a vector in Rn, take the norm and just do that integration, finite integration, Riemann integrations a to b gamma prime t dt. Okay, so one can have it, since my curve is piecewise smooth, then this integral exists and this is nothing but the length of the curve. So this is one of the applications of the concept of derivative of vector valued functions of real variable given. So this is the one of the applications. That means talk about a smooth curve or piecewise smooth curve, then it will have a parameterizations. It is a function from some subset of R to Rn. Okay, and since it is piecewise smooth, that means gamma prime t exists on the interval closed, it's a parameterization from say closed interval AB to Rn, except finitely many points in closed interval AB, it is actually differentiable. Okay, once it is differentiable, it is a vector in Rn, so you can make sense the norm. You just take the norm and you do integration, the value of the integration is nothing but the length of the curve. One example, just see. So find the length of the curve C gamma t is equal to cosine t sin t t. Okay, so you have to talk about the derivative. Okay, so of course, what is the derivative? Each of the component functions are very nice. It is a sine function, cosine functions, and we have functions. Okay, so what is the derivative? Derivative is minus sine t, cosine t, and 1. Okay, so what is the norm? Norm is nothing but, okay, I think it's 0 to 2 pi is also fine, because open also you can take. Okay, so gamma prime t is this vector. What is the norm? Use the Euclidean norm. This is the square root of this object, which is nothing but square root of 2 for all t in between 0 to 2 pi. That means what is the length? Integration 0 to 2 pi square root of t do t, which is nothing but square root of 2 times 2 pi, which is 2 root 2 pi. I think that's it. Okay, so I think I should stop here. So that means one of the nice applications we have seen is that if I have the notions of differentiability of vector valued functions of real variable, then if I take a piecewise smooth curve in Rn, or in particular in R2, R3, then I can talk about the length of the curve, because I know the notions of the, because once I have a piecewise smooth curve, then I will have the corresponding parameterizations, right. Parameterization is a map from some subset of R to Rn. So, and I know the notions of differentiability of this sort of functions. So, you have the notions of differentiability, then you will have the vector of gamma prime t, again it will be a vector in Rn, take the norm of this piecewise smooth, so that means start with a piecewise smooth curve, get the parameterizations, you know the notions of differentiability, find the derivative, take the norm and do the integrations from the a to b if it is a parameterization from closed interval a b to Rn. And if that the value of the integral is nothing but the length of the curve. I will talk about more examples in my next slides. So, but I think there are a couple of kind of nice applications, we will see those concepts. I think in next lecture I will talk about a little bit more. Okay, thank you.